L2 with decay minus 2 minus Q. Now the important thing is that the dual space of this space, which would be the domain of L star, is actually L2 with decay 2 plus Q minus N. Okay, so basically when you impose a weight, the dual space, the sign of the weight changes, but in this case we're working on Rn, which has some volume growth, so that gives you a minus N there. And so that dual identification comes from the just the pairing. If I take a function in that space F1 and a function in that space F2, then I have the L2 pairing bounded by just from the Schwarz inequality, the product of those corresponding norms. Okay, and so in particular, since I'm assuming, if I assume Q is strictly less than N minus 2, then S, which is N minus 2 minus Q, which is the number minus the number that appears there, is strictly positive. Okay, and that's why, and so in particular I can get the injectivity rates. This bound is simply false if you take Q equals N minus 2. Okay, and so that's really the reason. So you have to weaken the decay in order to get injectivity, the adjoint operator. Once you do that, you can, it's some work to do it, but you can carry out the linear theory and then the nonlinear, the Picard iteration also. So that's sort of one of the important punchlines. There's actually one other punchline too. I'll just say in the last minute. I think I have 1 minute. So actually, people have studied for a long time the question, the scalar curvature map. So you take a Riemannian metric and look at its scalar curvature, and then you can try to understand that as a differential operator. So in particular, we want to say that if the differential is surjective, then you can get an isomorphism between metrics and scalar curvatures under appropriate conditions. Okay, and so that actually, as far as I know, there was an early paper in 1975, Fisher and Marsden, which looks at that just for compact manifolds. However, the methods used there, and it comes in here too, is that when you do that procedure, you actually lose two derivatives. There's a derivative loss. So that operator, so this operator L star, I have it written back here explicitly. This operator, so it's a biharmonic, the double Laplacian, but there are coefficients here which, so this coefficient depends on 4 derivatives of the metric you started with. So we start with a metric, then we lose 4 derivatives on the right hand side here. Then when we solve for u, the metric deformation is L star u, which is 2 derivatives. So we lose 4 derivatives and we only gain back 2, and so there's a loss of 2 derivatives in the process. And so for that reason, it looks like you have to assume more differentiability, like 4 derivatives in order to get a C2 solution. And so in fact, we also managed to avoid that here. And so the basic idea is to, so it really is just a question of how you parameterize solutions. So this is a very underdetermined system, so there are many different ways you might try to parameterize solutions of it. So the Fisher-Marsden way to do it is to use, L tilde star u as the way of parameterizing to make that determined problem. But in our case, we have a nearby metric which is Euclidean. So our metric is actually quite close to Euclidean. So instead of using parameterizing in terms of L tilde star u, we can look at L star u. And so then we can write L tilde h as LL star, that's the Euclidean one, and then the difference between the two operators. It turns out by doing that, you save the loss of those derivatives, and that's why we prove the Sharp theorem derivative-wise. In fact, there's also a paper, Crucial and Delay, where they use a smoothing procedure to try to account for the derivative loss. But actually, Crucial tells me that their paper still needs more derivatives. So I think this procedure is a good improvement on the good remedy for that problem, at least in this particular setting. Okay, so since I stopped a half an hour early yesterday, I can go 2 minutes over. So it's not bad. Yeah, so actually the sort of most common, there are several different approaches between that. The most common one is called the conformal method. And so what you can do, so the idea of that actually produces data which tends to be to leading order like a slicing short shielded curve. And so what it does is you specify the, well, so the simplest case, if you're just solving scalar curvature 0, you specify a conformal class of metric, you conformally deform the metric. But there's an analogous thing for constructing data with general data. You can specify a conformal class of metrics and a mean curvature function and a transverse traceless tensor. So the sort of trace-free part of the second fundamental form. And then you can write down a determined elliptic system for the constraint equation. So 4 equations and 4 unknowns. And so that's an elliptic problem. And in some cases it can be solved. Actually, it's only known, it only really works when the mean curvature is constant. It's still an outstanding question as to how to handle the general case. But certainly using that method, you can construct a lot of initial data. And then once you have initial data, you can use this kind of procedure to I should say there are other very interesting ways of constructing initial data too. Like Bartnik has a way called the method of quasi-spherical foliations. And the idea is to start with a surface and some data, and then find a solution as it turns out the constraint equations are an evolution equation. And you look for a solution which is foliated in a specific way by spheres usually. And that actually has been very useful too. For example, the Shi-Tan theorem in about quasi-local masses uses that idea.
Understand the positions before class should be already ready.